Hi, everyone. Thanks for joining our Harnessing Value from Data in Motion in Real-Time webinar today. My name is Ian Gomez, Audience Marketing Manager here at DataTorrent. Joining us on the webinar is Mike Gualtieri, Principal Analyst at Forrester Research, and Larry Neumann, SVP of Marketing at Solace System. Key items we will cover today are trends in big data, why enterprises need to have a data in motion strategy, a primer on real-time streaming analytics technology, how streaming analytics is different, how your infrastructure requirements change for data in motion versus data at rest, architecture considerations on selecting real-time streaming analytics platform for your data and application needs, and real customer use cases finding insights from data in motion and building next-gen apps with DataTorrent's real-time streaming analytics platform. Here are some logistics regarding the webinar today. This webcast is being recorded. It will be available after the session has ended to watch again and share with your colleagues who were not able to attend our session today. Please submit your questions throughout the session. You can submit your questions via the Questions tab in your console, and we'll be happy to answer them after the presentation is over. Lastly, feel free to click the Attachments tab below to view more relevant information regarding the DataTorrent solution. Without further ado, I'll hand it over to Mike. Mike?
Thank you, and hi everyone. My name is Mike Gualtieri, Principal Analyst at Forrester, and I cover advanced analytics and big data. Thought we'd start with the business priorities, right? Because everything has to be put into the context of what businesses are trying to achieve. And we know from our general information that customer experience continues to be a top priority, followed by product innovation, of course, reduce costs and improve the overall ability to innovate. And we're seeing that come from harnessing more data, and that's what's been behind the big data trends. Now, these improved customer experiences have three characteristics. They have to learn about customers as individuals, their characteristics and behaviors. It has to detect what those customers want and need in real time, and then adapt those applications to serve the needs of an individual customer. So to create applications like this, you need two primary things. One, you need a whole lot of data so you can learn about these customers as individuals, not as broad segments. And the second thing you need is you need to be able to capture data in motion so you can adapt applications in real time. Now, there's also another trend emerging, and that is IoT, Internet of Things. And you can see here that 82% of enterprises are at least interested. Fewer are using it, but even more are planning, and a lot are interested. So you can see sort of across the board a broad interest. And likewise, IoT applications also have to learn about the individual devices, the systems of devices, detect the context in real time from data in motion, and then adapt those applications to improve the overall benefit of that IoT application. So with this as a backdrop, what companies need to achieve this is insights from data. And there's a characteristic about data that we often don't think about, and that is that it always originates in an instant, right? If there's a transaction, it originates in an instant. If there's a click, if there's a sensor reading, it always originates in an instant. The problem, however, is that most analytics and insights on the data is usually done much later. The data is collected, it's moved, and then it's analyzed. That's in-motion data, and all data starts off on in-motion, but most companies are not capturing it or analyzing it until potentially it's too late to use that data. And we call these perishable insights. And if you think about what perishable insights are, data creates value through analytics. It creates those insights, and you have a certain amount of time to act on that data. And there are four main types of insights. There's real-time insights, and that's from data in motion. There's operational insights that might not be as perishable, but also can benefit from data in motion. There's performance insights, which are like KPIs, how did the business perform? And then there's strategic insights used to make broader decisions. Should we hire a bigger sales force? Should we make an acquisition? Where should we put this store? So contrary to what many people say about data losing value over time, in fact, data can be valuable at each one of these stages. Unfortunately, what most companies ignore is that real-time insights, those very real-time insights that are needed for IoT apps and to create those customer experiences. And you see here that data, it typically originates, analytics is performed sometime later. You may or may not get some insights. You make a decision on those insights, whether it's automated or human, and then you take an action. And the problem is, if you don't compress that time frame, you could potentially be making poor decisions. You could have outdated information. So what companies have to do is compress that cycle of data to analytics, to insights, to decision, to action taken. And one of the best ways to do that is by analyzing data in motion in real time. The key question is, why wait, right? So now some people get caught up on what it actually means to be real time. And real time means highly perishable. So in the context of a mobile app for a customer, when they walk into a shopping mall, real time might be 30 seconds, right? Clicking on an online ad, it could be a matter of milliseconds. A temperature spiking could be a minute, or it could be a few seconds if it means shutting down a machine. So there's all these different degrees of perishability. So all businesses have some sort of real-time need, but that definition doesn't necessarily mean right now. It's basically real-time perishability. So if you look at that cycle and some of the examples, here are a few examples of the time to act. So really, the nature and need to analyze data in motion is based upon how much time you have to act. So you can see in this example here, real-time insights, say a customer shopping for furniture online, you might want to recommend cleaning supplies. That needs to happen instantaneously as they're browsing, right? At some point, you may look at the profitability and you want to optimize that price, lower it, or raise the price. Performance insights, you may look at a demand forecast and you want to increase your inventory. And finally, you may want to expand that line. That would be an example of a strategic insight. So you can map these types of insights and actions to your business as well. Now, one of the ways we capture perishable insights in real time is through streaming. And streaming analytics is a technology that can detect and act on the real-time perishable insights, the data in motion. And the definition of streaming analytics is tools that can filter information that in motion, aggregate in motion data, enrich it with other contextual information, and especially analyze it. And it has to be able to do this from multiple disparate live data sources, and it can identify those patterns. It can identify urgent situations, those insights that it can then use to make a decision to automate immediate actions in real time. And if you think back to customer experiences and the IoT applications, there's a lot of applicability here. Now, all forms of advanced analytics are surging. And if you look at this chart here at streaming, where we show sort of the adoption between 2014 and 2015, big increase in adoption from the low 30% to the low 40%. So that's a market increase over 1 year. What's interesting is that less than 50% of companies still report that they're using it. So there's still a big opportunity for firms to analyze in-motion data. So some of the applications is for personalization is understand in real time what a customer is shopping for, but then understand her very specifically and what should you do. Should you make her an offer for a discount, or should you send her a gentle nudge to make her buy? These are all important things to do in real time. Now, you may not want to send an offer because you may know that this customer is likely to buy anyway, and you've just saved yourself the 10%. Other applications in real time, obviously an IoT application, looking at sensors in tires if they're slipping, If it's slipping in this car, what if it could warn drivers a mile behind that there are slippery conditions? And even telecommunication cable companies are recording every button that you press on that remote control so that they can at some point show an ad that's very relevant and predict who's watching. So all of these types of perishable insights, real-time perishable insights, come by analyzing data in motion right now. And to do that requires streaming analytics technology. Now, streaming analytics is a little bit different. So it has to do two things, because typically when you think of collecting data, there's some ETL process, right? You have to enrich it or transform it. You have to put it in a format where you're able to analyze it. So streaming analytics has to have continuous ETL built in. As that data is flowing by in motion, streaming has to be able to do what you would think of as common ETL-type functions. But the heart and smarts of streaming analytics is the continuous analytics, the ability to correlate information from multiple streams of data, the ability to look at location and motion data, the ability to aggregate in a time window, to detect patterns, and then also to embed business logic and rules, and finally, to help those upstream applications make a decision and act on those analytics. So this is very different. It's almost a misnomer to call streaming analytics analytics, because it's actually not just analytics, but it's an execution engine too, and it's essential for capturing data in motion. Now, when you look at this technology and how it fits into the application process, and especially back into those requirements I mentioned on being able to learn about customers, learning about systems of IoT devices, this is what a modern application looks like that infuses real-time analytics. You can see that we need streaming analytics at the top, and this is always on, and this is providing that real-time context. It's looking at those patterns. It's understanding who this customer is, and it provides that application logic, that real-time context. But you also see below there's a machine learning function, which typically works in a batch mode to create models that ultimately insert learned logic into the application, and the streaming data feeds that process as well. So you're looking here at what a modern application needs to look like to take advantage of data in motion, to learn from that data over time, and then provide an application that can adapt. So let's look at some of the properties, some of the characteristics that you should look for when you are looking to buy or acquire a streaming analytics platform. Well, the first thing is, it has to be able to ingest information that's both structured and unstructured from multiple sources in real time, right? Because that's sort of a basic tenet of streaming, is that it can connect to these live sources, these real-time sources. And it's not just about structured, it's about both, right? And it has to be able to do this from multiple sources in real time. It has to scale to handle any volume and velocity of data. I mean, you can imagine those customer experiences we were talking about can be mobile experiences, and they could be millions of users simultaneously or even hundreds of thousands. So a streaming platform has to be able to scale horizontally to be able to do that, and also has to be able to take spikes in the throughput. And it obviously isn't just about ingestion, and this is a big mistake that people make when they think about streaming. There is such a thing as stream processing, where you're just ingesting that data and storing it later. But what distinguishes streaming analytics from stream processing is the ability to do both, the ability to ingest, process that information, but then also to analyze it. And it's a real big architectural difference between just taking data in and storing it somewhere versus analyzing it. You need an architecture that can do that analysis at extremely low latency at very high volumes of data. Now, as I showed you in the application diagram, streaming analytics is a bit of a misnomer, right? Because it's not like some batch process you're running tomorrow or at the end of the month. It's always running. It becomes part of the application. and thus it has to be fault tolerant and mission critical. So as it's ingesting, as it's doing this analytics, and as it's scaling out among a cluster of nodes to handle that scale, any one of those nodes goes down, it has to keep running. So it has to be fault tolerant as well. As I mentioned, streaming is a little bit different. Thinking of streams is a little bit different. So you need tools that make it easy to manage and monitor that platform just as you would other architectural components. So you don't just want this to be some jar file you toss in a directory somewhere. You need to manage this just like you would manage any other set of services if you're going to incorporate this into applications. And in addition to embedding the results of streaming in applications, many of these streaming analytics platforms also offer tools to visualize those insights from data in motion, because sometimes those real-time insights come from dashboards that people are monitoring. Sometimes it comes from embedding that as well. So streaming analytics provides a real opportunity for companies that want to create those next-generation customer experiences. It's an essential component of all IoT applications. So, think of streaming analytics in the first place to capture data in motion. And remember, data originates in an instant, and it's usually analyzed much, much later. All right, so streaming analytics is essential to capturing and analyzing that data in motion. You can use that capability to then detect and act on those real-time perishable insights. And those are the perishable insights you will identify that will make your application a lot smarter, a lot more individualized to a customer or to that system of IoT devices. And then finally, use streaming analytics to create real-time applications. There's no reason why every and all applications should not be a real-time application and take advantage of all of that data in motion. So I'm now going to hand this off to Larry Neumann, who will now take you through some real-world case studies. Larry, over to you.
Thanks, Mike. Thanks, Ian. Hello, everyone. My name is Larry Neumann. I'm from Solace Systems. We provide scalable infrastructure for all kinds of real-time data movement. Thank you very much for inviting me. So Mike talked a lot about what's different about real-time analytics and the kinds of new decisions that are made possible when you get your time cycles down to shorter and shorter periods of time. I'm going to talk more about how the infrastructure changes as you move to this real-time analytics environment. And at the end of the day, the stress on the infrastructure, the stress on these analytics engines comes from the sources of information and all of the big ticket changes in the IT environment right now are all driving enormous increases in data volume. If you look at the cloud, for example, the cloud is forcing processing to be more distributed in more places. Data has to move from place to place more frequently, often over long distances. Big data we're going to talk about a lot in really this whole session, so I'll skip forward to mobile and Internet of Things. They introduced the notion, Mike talked about a little bit, of sort of fanning in and fanning out of data, so collecting information. You think about something like Google Traffic, where they're consolidating data they collect from everybody's phones when they're logged into Google to figure out whether traffic's flowing or not. That's a massive fan-in application where millions of data points are then turning into a set of analytics in the back end that are driving that same data to fan back out to all the screens that are displaying the traffic information. And the Internet of Things is really driving the cross-property of collecting or automating down to prices we've never seen before. You can put a sensor, a very cheap sensor, on something and have continuous information where previously, if a human being were doing it or some other process were doing it, it was very expensive. If you look at something like a meter reader who used to come to your house once a month, it's expensive to send the guy around the neighborhood and have them look at the side of your house and figure out how much electricity you used since the last time they were there. but one day a smart meter gets installed, and now you've got the ability, and it's really up to the energy company then to turn up the dial and say, well, okay, I want that data once an hour or once a minute or once a second, depending on what their goals are over time. And you can be assured that over time that rate of data input from these different sources is going up as well. But it's the sensor that makes it possible, and those sensors are infiltrating just about everything we do. Of course, enterprise integration it is not gone away. That's the sort of the core systems that track your manufacturing, your customers, your orders, all of the different aspects of being an enterprise. Those systems have often been around for decades, and the data volumes through those are also going up simultaneously. You look at all of those, and any one of those in its data growth would put stress on an infrastructure or an analytics challenge, but all of them happening at the same time is really giving IT or operations teams fits. And at the very basic level, Mike talked a little bit about this as well, but at the very basic level, what's unique about real time in this area is that each event occurs in an instant, as he said, and becomes a time series. So whether it's a single device that's generating data every 5 seconds, or it's 1,000 or 100,000 events that are all consolidating together to make a stream, each one of those instances becomes a stream of information, or many streams of information that need to be processed differently. Each event is its own unique item, as opposed to, say, the days where we would, grab an hour log file and then load that into the analytics engine, and then we've got an hour's more data to work with. In the streaming case, we have an instance more data. Each time a message is processed, it's the next instant and the next message, and that could be 100 items per hour, or it could be 1 million items per second, or tens of millions. It really depends on the use case, and that the job of the infrastructure is to be able to handle at least the rate of everything above it, because all those applications above, whether they be streaming analytics or data archiving engines or whatever, are all relying on the infrastructure to get that data in place. It's a very simple concept. There's data streaming, and then it's going to be consumed by something like these real-time analytics engines. But the devil's in the details, of course. There are many, like every other kind of architectural choice, there are many ways to stream data, and they've all kind of unfolded over a period of years and decades. So the legacy environment, possibly where your crown jewels of your enterprise exist, are largely behind closed proprietary protocols that have been around forever. They're deeply embedded in those systems. Makes sense to use them because it's difficult necessarily to get in and change code. So you pull the data out in the format that it has been designed to come out. You've got a slightly more modern system. You might have something like JMS or AMQP that's doing the same type of role. In the Internet of Things, the messages tend to be a little bit more lightweight and transient. So a set of lightweight transient protocols have emerged that make it easy to do those kinds of message streaming. When you're ingesting into big data, there's oftentimes that's happening in bulk, or it's happening at very high volume. So some high volume protocols have emerged there. In the mobile world, streaming to mobile, there's protocols like WebSockets. People use REST for inbound from mobile and so on. And then, of course, cloud has its own set of protocols for how you move the data between components of the cloud. And so there's a lot of different choices, and if you look at just one application, we've got an oil and gas customer, for example, that has thousands of sensors on their oil pipeline, and they're feeding all those streams from each of the sensors into a real-time analytics engine that's also consuming some information about the current price of oil and in the market. Their current production rates can be determined based upon all these sensor data, the aggregate of all that sensor data, and that leads to a dynamic pricing outcome so that they can literally optimize to a few more cents per barrel by dynamically pricing instead of pricing by the day or by the hour. And so they can continuously change based on supply and demand. Now that data has to get pushed out to their ERP system, and then has to be synchronized to the cloud, where their trading partners can access the current pricing possibly dashboards on web or mobile. And if you just take that one application, and it basically includes something from every column in this picture. You've got everything from your ERP system to your cloud system to streaming out to mobile and so on. And a given microservice may only have to work with one of these, but the application has to work with all of them. And so the trick is many applications need many different ways to communicate information, but most technologies only really support one. So you grab an open source protocol, it probably does one of these things. You take your legacy protocol, it only does one of these things. So it is a bit tricky to get an infrastructure, an end-to-end infrastructure that not only can do all these things, but then can keep all these things functioning at the right scale and so on. So if we go forward, that sort of leads us into this idea of scale and on-demand scaling. And a good infrastructure really has to be able to do that as well. It has to be able to identify when data rates are going up and scale horizontally. So if you've got one bus on the road and suddenly you've got 3 times as much traffic, you put more buses on the road. That's the same idea. If you've got an infrastructure that's at one capacity and you have to scale it up to several more, sometimes you can do things that way in a stateless way where everything is independent and having many engines sort of doing the same thing works really well. And other times you sort of need contextual consistency between messages. In that case, it makes more sense to have a smaller number of engines that can scale vertically. And ideally, an infrastructure or an analytics engine that can do both of those things is extremely valuable. A separate concept from elastic scale is this idea of volume spikes, which is where something happens out of the ordinary. Something you weren't expecting is generally when a volume spike causes problems. So that may be something like, you were hoping Pokemon Go was going to be a hit, but you didn't quite anticipate that 25% of people with cell phones were going to have it inside of a week. And so suddenly you've got an infrastructure that has to scale way beyond what you anticipated, and so that's a spike that has to be dealt with. Sometimes it's caused by a component in the system slowing down and causing back pressure on the systems that are upstream, and that can create all kinds of additional problems. Or sometimes there's a simple outage where maybe a process is being rebooted and nothing can happen for a minute or so, but when that process is completed, you want to pick up where you left off a minute ago and catch up before you continue on with the real-time processing. So you need a buffering system of types to be able to handle these spikes. And just to provide an example from the financial markets, here's a picture. I don't know if you can read the details, but this is the foreign exchange market and a typical daily rate of foreign exchange. And every day something happens in the foreign exchange markets where an unemployment number comes out or a economic indicator is released, and it might cause a 25 to 50% variance depending on how much impact that has on a given country or a given currency. But every once in a blue moon, something happens, like when the Swiss unpegged their currency from the euro. It was a bit of a black swan that nobody was ready for, and all of a sudden there was a 300% surge in trading. And just a couple of weeks ago, the Brexit vote, the unexpected outcome of the Brexit vote, caused the currency markets to go crazy and the pound to drop dramatically against all the other currencies in the world. And so the foreign exchange systems, which are sort of plugging away, doing their thing every day, have all of a sudden 4 times as many customers at the door the next morning, and literally in an instant. And so the thing about spikes is spikes tend to, they're a cascading problem. It's not the case that you have 4 times as many people trying to make a trade. It's that comes with 4 times as much foreign exchange quote data, and it comes with 4 times as much risk management updates that have to occur, and 4 times as many downstream systems that are impacted, and so on. So the infrastructure, of course, has to handle all of those componentries, and each one of those components in the chain have to keep up with this higher data rate as well. So it becomes a very serious problem in terms of how you cope with the data spike and how you make it so it doesn't create outages or too much trouble in the infrastructure. And then there's the LAN versus the WAN aspects, the pure physics of your physical links. This is the infrastructure always has to factor these things in. If you've got two machines that are in the same rack and they have a wire separating them, it might be a couple of microseconds to get data from place to place. But if you're going from Asia to New York, it's a completely different set of properties that have a high, it's because of the speed of light, they have a high latency. And it's very expensive to have something like the same capacity, so you probably have much more limited capacity. You just look at those two pictures on that page, and you imagine a fleet of 1,000 trucks have to go down those two roads. You can imagine inside of a minute you could get your 1,000 trucks through the picture on the left, but 1,000 trucks unleashed on that mountain pass could literally take the whole day to clear. It would be gridlock. Because each message can only go as fast as the one before it, and any one breaking down is going to cause all the trucks behind it to back up and so on. And it's kind of like that with LAN and WAN decision making. If there's a very real property related to cost that you have to factor in, like let's say that you're an e-commerce company, and I buy sneakers every 5 months, and you want to try and convince me to buy them after 4 months. So you do all this analysis on my click streams and my behavior, and your end goal is to sell me a $60 pair of shoes with a $1 margin. It doesn't necessarily make sense to take my click data, my megabytes of click data, and send that over an expensive WAN link in real time. But if I'm a manufacturing customer and my contract manufacturer is sending quality data to my quality center so that I can identify when that manufacturing facility is out of spec and shut down their line before they waste hundreds of thousands of dollars in physical inventory and goods that are going to have to be scrapped, that is a very high volume set of data, and that probably does make sense to go and buy a very dedicated high-speed WAN link. And those same kinds of ideas apply to the cloud as well. It's what you put where and how valuable that data is, and what the economic impact of the analysis is all a factor in how you choose to lay out your infrastructure. And the last thing I wanted to talk a little bit about was class of service. This is a well-known concept in the infrastructure space. It's each given set of data types has a different set of behaviors that it wants to have applied to it by that infrastructure. So if you're a sensor read, like we talked about before, and you're going to send in the current temperature, and there's another sensor read coming 5 seconds later with the current temperature, then it's not absolutely essential that every one of those gets through. You can do valid analysis with gaps in that data. But if it's an order that showed up at the Amazon website, you absolutely don't want to lose that, because it impacts customer service, it impacts the inventory update that you made, and so on. So you absolutely have to get that order to its destination and off into fulfillment and so on. And then if you're a banking transaction where you're moving money from one account to another, that's a completely different thing, where all of them have to happen, or you have to have the ability to roll back so that none of them happen. And each one of those are examples of classes of service. Sometimes that an individual request is going to come with one specific reply, and sometimes you want to completely decouple your producers and your consumers, like in Publish Subscribe, where you can add and subtract people who are creating and consuming that information on the fly, and that gives you a nice decoupling mechanism. So there's literally a book of, I think it's 736 pages of all of these different patterns of exchange depending on what you're trying to accomplish. And I think many of you will be familiar with this book, but just about every architect has it on their shelf or on their Kindle. And it really underscores how hard you have to think about each one of these exchanges and to apply an infrastructure class of service so that the right thing happens to the right set of streams. So I've talked a little bit there about considerations for infrastructure. I wanted to spend a few minutes here and talk about some specific use cases. And I picked use cases where real-time analytics were at the core of what was being accomplished. First one is the Smart City Initiative at the City of Singapore. I think it's generally understood that Singapore is out in front in terms of implementing smart city initiatives. They've got all kinds of stuff underway, from smart buildings interacting with each other and home health care monitoring of the elderly. They've got outbound communications to all their citizens in standardized ways so that they don't have to have 100 different websites to go to find out, local, municipal, so on, et cetera. Smart transportation, where systems and vehicles can talk to each other. That's actually the one that we're most involved in. I know the most about, and I'm going to talk about here today. But if you're familiar with Singapore, it's really just a big city that's also a nation, and it's a very congested place. There's not enough roads, and there's too many people who want to be on them. And so they've put some massive disincentives in place to own and drive a car. So, for example, a car that would cost $30,000 or $40,000 in North America costs about $150,000 to $200,000 to buy that same car, like a Volkswagen, in Singapore. And then once you have your car, you have to spend anywhere between $50,000 and $70,000 a year just to license it for use on the road. So those are pretty massive disincentives to own and drive a car every day to go to the office. But it does put enormous emphasis or a requirement, an incumbency, if you will, on the government to put a very good public transportation system in place. And so they've put some very advanced public transportation mechanisms in place. They not only do they track where their physical assets like a bus are, but they put sensors on them that do things like measure how much weight is on the bus, so they can approximate how many people are on the bus, how much carrying capacity it has left, and then they can do things like use cameras to assess approximately how many people are waiting at the next bus stop. So when is the bus going to have to turn away people? And how can they elastically scale by introducing new buses into the same line? They have rover buses that can be introduced where they're needed on the fly and keep the consumer flow moving and keep people happy getting to their destinations on time. And similarly, they do the same kind of thing, where in North America we have these automatic toll collecting devices in our cars where we drive under a gantry and we get charged a price to go over a bridge or onto a toll road. The next level beyond that in Singapore is kind of more like the way Google Maps works, where they're doing constant ongoing supply and demand analysis of how many cars, how congested are the roads, and they're incenting people to take the less congested paths based upon billing. So they have automatic charges on these different roads that are adjusting and adapting all the time and giving the information to the consumer as they hit an intersection how much it's going to cost them to go each way. And similarly, instead of having parking devices everywhere you stop your car where you have to go and get a ticket and put it on your dashboard, they just have that same device in the car, figure out where you stopped and for how long, and bill you accordingly based upon the parking space that you took up. So it's pretty fascinating, and it's the kind of advance that I think we're going to see come to every city with real-time streams going into real-time logistics and analytics engines, and then having those come back out in the form of a better use of the supply and demand nature of the city. Another example, capital markets. A large customer, a banking customer, wanted to do algorithmic trading. They were already a Solace customer, so they were sending out millions of events a second, and they tried to write their own code that essentially couldn't consume enough data. And so we ended up sharding the data so that, if you have a problem where you're tracking maybe the price of a Russian oil company versus the currency of the ruble versus the euro, and you're looking for variances whereby you can get in there and make a few dollars when they come out of step, it's relatively easy to take millions of messages a second, turn them into thousands of messages per second that just handle those few instruments, and then write an engine that makes decisions. But if you want to have a general purpose engine that can take in the entire feed and then set up what-if scenarios across the entire feed and possibly execution scenarios. That's really what they were trying to do, and they brought DataTorrent in to do that ingestion, to basically receive the ingestion. And DataTorrent's got some unique features that allow auto-scaling to go up with ingest rates, so many ingestion points that are feeding the same in-memory grid, so that the data can get in fast enough to be analyzed. They also found that once they could do that, they were able to set up another layer of analysis where they were looking at the trading volumes coming out of the algorithmic engines, and they would automatically scale up the downstream systems as well. So if it's a quiet period, you can sort of have a small number of downstream systems handling the trades, and then as trading activity ramps up, that same analytics engine was determining that we need more of these back-end systems downstream to pick up and make sure that trades can get through. They also did a replay system so that if they wanted to go back and do what-if on a set of messages, by replaying them and sort of pretending the day was happening all over again, they could do that as well in the same sequence. So I'm sorry, I didn't click my bullets there, but I'm going to move on to the next example. The retail banking. Another customer was a retail bank, and they wanted to do fraud detection. And they had a series of events. They called them fingerprints. Things that are unlikely to happen in sequence that indicate fraud. And the best system that they had was a Hadoop-based system that allowed them to capture the events, get them indexed, get them analyzed, and in roughly tens of minutes, roughly 10 minutes, they were able to identify when a fraud event occurred, and they'd have to track down the person and say, did you really make this withdrawal? Did you really make this credit card charge? And oftentimes they couldn't get the person because they're no longer in the same place that they were when they made the event. So their goal was to improve that by 20 times in one step to get that down to sub-minute. And they brought Solace and DataTorrent in, and basically we took the sample set of those fingerprint analysis points together. We worked as a team, and we're able to show them at 10 times their current transaction volumes a sub-500 millisecond response time, where they could identify their fingerprint patterns on a very, very high volume of transactions, met the requirement, and sent them. Basically, they were able to identify fraud in real time as it was happening, which was a big improvement from even what they thought they were going to get out of their next generation system. So that's another good example. And the last one I'm going to talk about here is a mobile carrier that had falling behind in customer experience. They were having a problem with dissatisfied customers, poor customer satisfaction scores, and they really wanted to understand. They've got all this incredible data. Every time somebody consumes a service, every time someone sends a text, they've got an event that appears in the back end that is identified with that account. Every time someone catches a wild Pidgey in Pokemon Go, that's some data consumed. It also tells them something about that person based upon the applications that they're using and the type of data and so on. So how do you take the scale of problem that they were encountering, where 6 years ago that might have been a couple 100,000 events per hour that were being captured, and it had scaled up into the 30 billion data points per hour. So how do you take 30 billion data points per hour and rationalize that to apply to improving customer experience? Of course, customer expectation only goes up over time as well. And so what did they do? They sucked all these basically they sharded the data into manageable feeds. They sucked it in for a set of users at a time, and they started to make decisions about, okay, so here's an area where we're having poor data performance right now. We know from history that causes people to churn and eventually, if that happens enough times, move on to another carrier. And so let's offer them a half a megabyte or half a gigabyte of free data for this month because, hey, we're sorry you've been having problems. We're working hard to fix it. Here's a half a gigabyte. They know that makes unhappy customers into happy customers. It seems like, oh, that's reasonable. They at least understand my frustration. And so that caused their customer service scores to go up. And they also were able to proactively identify behavioral patterns of their towers and say, based upon what we're seeing in tower number X, we think that this component is going to fail 3 days from now because there's the same pattern we've seen 100 times before, and they can proactively send someone out to fix it before it fails and keep data service quality high. So those are just a few examples that I wanted to talk about today of real-time use cases, and I will turn it back over to Ian.
Thanks, Larry and Mike, for that great presentation. We have some questions in the chat window that we'll go ahead and answer. So our first question is, it's for Mike. How does streaming work in conjunction with Hadoop?
Yeah, so I mean, generally streaming needs to work in conjunction with many different platforms. What sort of makes this a unique question about Hadoop is that is often a landing zone for a lot of this data and all of the analysis that follows. So some products can either connect to Hadoop as a data source. Other products can run under the Hadoop environment. So that's one of the things that makes Apache Apex so interesting, is that it was designed from the ground up to actually work in Yarn, which is the resource manager for Hadoop. So streaming can work external to the Hadoop cluster, or if it's designed to do so, it can actually operate in conjunction with the same cluster.
Awesome. Thanks, Mike. So I have another question for Larry. Larry talked about the different kinds of messaging causing the infrastructure to become fragmented. How does this get resolved?
Well, I mean, that's a bit of a tricky question. There's a lot of history in how it got to be that way in the first place. I mean, the different options for messaging have unfolded over a period of decades, and so it makes logical sense that there would be legacy protocols that have been around for, like IBM MQ, for example, has been around forever, embedded in mainframes and other systems. And then similarly, as we get to more modern things like IoT has different requirements than enterprise systems. So somebody came up with a very lightweight protocol like MQTT, and so each type of application has a protocol that it rallies around, and the assets and the companies that work in that on that problem all kind of use that protocol. So it'd be really nice if everybody used the same. Let's say everybody standardized on MQTT for everything. So I'm going to switch all my enterprise and my big data loading and everything to MQTT. Well, it's not the right protocol for big data loading. It's not the right protocol for doing transactional updates to a banking system. And so you kind of end up with a requirement that you have all these protocols in some form. The question is, do you really have to have a separate tool for each one of them? And as a vendor, that's kind of where we focus, is we take the open protocols that exist in the market and try to consolidate them into one product. So if you've got requirements around JMS or WebSockets or REST, terminating REST connections, or things like AMQP is something we're working on. If you want something that can do all of those things in one bus, one backbone, and can bridge between the environments, so maybe you terminate a REST connection, and then a piece of data or a message comes in via REST and goes out via MQTT, and you don't have to build a bridge in between. The broker can kind of just take care of that. So being able to do many things brings a lot of value in consolidating these environments into one thing to scale and one thing to manage instead of many. So that's the approach that we advocate. But that from a governance perspective, everybody's kind of got to look at what they've got and how to keep it up and running.
Great. Thanks, Larry, for answering that. We have time for another question. I'll be directed towards Mike. What is the difference between stream processing and streaming analytics?
Yeah, so streaming refers to data in motion, and that's coming from the sources, a lot of the connectors that you were just talking about. So stream processing is the real essential difference is that stream processing has to do with ingestion and maybe some light transformation of the incoming data. And streaming analytics can actually perform analytics. Now, the key difference here is that streaming analytics platforms are extremely stateful. So they cannot be stateless, because if you are aggregating, say, a temperature over a 1-minute period, you need to keep the state of that temperature. And if you're doing that across thousands of sensors, you need to keep a whole lot of state. So streaming analytics, to actually perform that analytics, is actually extraordinarily stateful. Another example is, say you're trying to detect a pattern of events. So let's just say an event A comes in, and if an event B comes in within 1 minute, then that's an interesting event. Let's just say that represents some sort of a fraud. Right? So think about that technically, what you have to do. Whenever an A comes in, you've got to store it somewhere. You've got to say, okay, I just got an A, and now you've got to wait 1 minute to see if a B comes in, right? If it doesn't come in, then you can throw that A away. But keep in mind, there could be many other A's coming in. So the key difference is that stream processing is very much akin to messaging systems that can do some light transformation, where streaming analytics is a whole different class of products, the ones we're talking about here, and it has to be stateful. It's the only way it can perform varied and sophisticated analytics.
Great. Thanks, Mike, for the clarification. So everyone, that concludes our webinar today. Special thanks to Mike and Larry for their time. Also, feel free to view our data sheet and free software downloads, including the DataTorrent Sandbox, Community, and Enterprise editions in the tabs below. Look out for more webinars by DataTorrent in the next few weeks. Have a great day, everybody.